Exercises on part 5, acid-base reaction and salty solution. Exercise 2, which of the following ionic solids produce a basic solution in water? To know the nature of the salty solution obtained, we have two methods. Method 1 is to look for the nature of the acid and the base that provide the salt by reaction, and method 2 is to study the interaction of the ions produced by dissolution of the salt in water. NaCl dissociates completely in solution to give Na plus and Cl minus. We don't have any couple acid base containing Na plus or Cl minus, so Na plus and Cl minus are spectators. KNO3 dissociate to K plus and NO3 minus, and by the same way K plus and NO3 minus are spectator. CaCl2 dissociates completely to the spectator ions Ca2 plus and Cl minus. So the salts NaCl, KNO3 and CaCl2 will give solutions neutral. So these salts are neutral. To note that NaCl, KNO3 and CaCl2 are strong electrolyte since no values of Ksp given. NH4Cl, which is a strong electrolyte, dissociates completely to NH4 plus and Cl minus. Cl minus is a spectator. NH4 plus react with water to give HCO plus, so NH4 plus is acid, and therefore the solution is acidic. NaCN dissociates to Na plus and Cn minus. Cn minus is the conjugate base of the acid HCN in the couple HCN-Cn minus, so Na plus is a spectator, Cn minus is basic, so the solution is therefore basic. So the correct answer is E. Another method to answer this question is to search for the nature of the acid and the base that provide the salts. For example, NaCl, the cation Na plus is provided by the strong base NaOH. The anion Cl minus is provided by the strong acid HCl, so NaCl is neutral. Same for KNO3 and CaCl2. If we consider NH4Cl, the cation NH4 plus is provided by the base weak, which is NH4OH, and the anion Cl minus is provided by the strong acid HCl, so the solution is acidic. In case of NaCN, the cation Na plus is provided by the strong base NaOH, and the anion Cn minus is provided by the weak acid HCN, so NaCN is basic. Exercise 12. State if a reaction takes place between the following species. We know first that we don't have reaction between acids and no reaction between bases. Between acid and base, we have necessary a reaction, and this reaction is advanced in the direction of gamma and limited in the anti-gamma direction. Between CH3CO and A and HCN, we have to do increasing order of pKa scale and determine the couples involved. The couples involved acetate, acetic acid, Cn minus HCN. Then we determine the species present. We have acetate and we have HCN. So we have a reaction, but since this reaction is in the anti-gamma direction, so this reaction is limited. We write the reaction CH3COO minus plus HCN gives Cn minus plus CH3COH. K of the reaction is equal to the concentration of acetic acid times Cn minus at equilibrium divided by acetate and HCN at equilibrium. So we multiply by HCO plus concentration and we obtain Kr is equal Ka of the couple HCN divided by Ka of the couple acetic acid, so K equal 10 minus 4.5. K of the reaction is less than 10 minus 4, so we can suppose that this reaction did not proceed, or we can say this reaction is non-spontaneous or very, very limited. Between HCl and NaH2PO4, so between HCO plus and H2PO4 minus, HCO plus and H2PO4 minus, we have reaction, and this reaction is advanced since it's in the direction gamma. We write the reaction H2PO4 minus plus HCO plus gives HCPO4 plus H2O. K of the reaction is equal H3PO4 divided by H2PO4 minus and HCO plus concentration, so equal 1 over Ka of the couple H3PO4, Ka1, so equal 1 over 10 minus 2.2 equal 10 to the power 2.2. So this reaction has a value of K less than 10 to the power 4, so this reaction is not quantitative. We say that the reaction is advanced. And K of the reaction is greater than 10 minus 4, so this reaction is spontaneous. So as a conclusion, we have a spontaneous reaction between HCl and NaH2PO4, but this reaction is advanced. Exercise 13, a monoacid HA of pKa5 is mixed with a base of pKb equal 5. Which of the following statements are correct? First of all, the acid HA has a pKa5, the base B has a pKb5, so pKa equal 9, since pKa plus pKb of the same couple equal pKw. Put the two couples on increasing order of pKa and determine the species present B and HA, so the reaction is advanced since it's in the direction of gamma, and HA plus B gives A minus plus BH plus. K of the reaction is equal products divided by the reactants concentrations at equilibrium, so equal 10 to the power 4. In A, it was proposed that the proton transfer reaction HA plus B is complete. This is false, since the reaction is complete if Kr is greater or equal 10 to the power 6, or delta pKa is greater than 6. And the reaction is quantitative if Kr greater or equal 10 to the power 4. B, the reaction HA plus B shifts strongly towards the product. This is true since the reaction is advanced and is practically quantitative since Kr is equal 10 to the power 4. C, the equilibrium constant is 10 minus 10. This is false. We calculated Kr equal 10 to the power 4. D, this is true. And E, the equilibrium reaction constant cannot be calculated without additional information. This is false. So the correct answers are B and D. Exercise 14. Consider a mixture of methanoic acid and its conjugate base methanoate, nitrous acid and nitrite, and we have the following reaction given pKa of the couples. 14.1, the equilibrium constant of the reaction taking place is, so we write the reaction, and the equilibrium constant is equal to the concentration of the products divided by the reactants at equilibrium. So HCOH times NO2 minus concentration divided by HNO2 and HCO2 minus. We have to transform Kr as a function of K of couples. We multiply by HCO plus. So HCO plus times NO2 minus divided by HNO2 times HCOH divided by HCO minus times HCO plus concentration. This is Ka of the couple HNO2, and this expression is 1 over Ka of the couple HCOH. So Kr is equal Ka of the couple HNO2 divided by Ka of the couple HCOH equal, so the answer is C. 14.2, calculate the value of K. K equal 10 to the power 0.6 equals 3.981, so approximately equal 4. The answer is B. 14.3, before the reaction, the initial concentrations are HNO2 initial equal HCO minus initial equal 2 times NO2 minus 2 times HCOOH. So calculate the reaction quotient K of the reaction, Q of the reaction. So the initial concentrations are equals 3 10 minus 2. That of NO2 minus and HCOH equal 3 10 minus 2 divided by 2 equal 1.5 times 10 minus 2. Q of the reaction at T equals 0 is equal to the ratio of the concentrations at T equals 0 between the products and the reactants. So equal 1.5 times 1.5 10 minus 4 divided by 3 10 minus 2 times 3 10 minus 2, Q equal 0.25. So the answer is A. 14.4, in which direction will the reaction take place? The system occur in direction 1, the system occur in direction 2, the reaction is complete, and D, the reaction is non-existent. To know the direction of the reaction, we compare the value of Q to the equilibrium constant K. So Q is less than K, So the evolution of the reaction will be in the forward direction or in direction 1. So the answer is A. Calculate the pH of the solution at equilibrium. First, we write the reaction between HNO2 and HCO minus. That gives NO2 minus and HCOH at T equals 0. The concentrations are C, C, C prime, and C prime. The reaction proceeds till the equilibrium. So at equilibrium, we have C minus X, C minus X, C prime plus X, and C prime plus X. We calculated previously Kr of the reaction, which is equal to 4. That means the reaction is not very advanced. So in this type of problem, X is negligible. So the reaction in direction 1 is not very advanced. The reaction in direction 2 is limited since K reverse equal 1 over 4 equals 0.25. So practically, since X is negligible, the concentrations of the species at equilibrium are equal to the initial concentration. So at the equilibrium, HNO2 is practically C, HCO minus practically C, NO2 minus and HCOH are practically equal to C prime. So in the solution, we have two free couples, HNO2, NO2 minus, HCO minus, and HCOH, and these two couples behave as free in the solution. So the pH is determined by each of the couple, so we can apply Henderson on the first and Henderson equation on the second. On the first, pH equal pKa plus log base over acid, and for the second, pH equal pKa prime plus log HCO minus divided by HCOH at equilibrium. We add the pH, so we obtain 2pH equal pKa plus pKa prime plus log NO2 minus divided by HNO2 times HCO minus divided by HCOH, and we said that NO2 minus is practically equal HCOH equal C prime, so we cancel NO2 minus with HCOH, and by the same way we cancel HCO minus by HNO2. So we obtain pH equal 2pH equal pKa plus pKa prime. That means pH equal pKa plus pKa prime divided by 2, and the pH is therefore equal 3.5, and the correct answer is D. To note that this relation can be applied directly without doing this proof. pH equal pKa plus pKa prime over 2 can be applied directly when we have the following conditions. Weak acid plus weak base, condition 1. Condition 2, no reaction or limited reaction between this weak acid and this weak base. Third condition, the weak acid and the weak base should have the same initial concentration. So when we have these three conditions, we can apply directly this formula, pH equal half pKa plus pKa prime, without doing, as we said, all this proof. 2.6, we prepare new mixtures with the following initial concentrations. HNO2 equal HCO minus equal 0.1, NO2 minus equal 0.1, HCOH equals 3, 10 minus 2, and we have several proposals. To know the advancement or the shift of any reaction, we calculated Q. Q equal concentration of the products divided by the concentration of the reactants, and this value Q is at T equals 0. So equal 3 10 minus 1 times 3 10 minus 1 divided by HNO2 initial, which is 3 10 minus 2 times 3 10 minus 2. So the value of QR equal 10 to the power 2. Now we compare Q to the value of K of the reaction. Q is greater than K, Q equal 10 to the power 2 and K equal 4. So Q is greater than K, so the reaction will shift backward in direction 2, and the answer is B. In C, it was proposed that the reaction is complete. To note that the reaction, complete or not, depends on the value of K, and it does not depend on the value of Q. Exercise 26. A solution is prepared by dissolving 1.24 grams of ammonium chloride, NH4Cl, into 150 ml water. So we have to calculate the pH of this solution. First, NH4Cl is a strong electrolyte that dissociates completely to NH4 plus and Cl minus. NH4 plus belongs to the coupled acid base NH4 plus NH3, so NH4 plus is an acid. Cl minus does not interact with water. We don't have any couple. HAA minus, for example, containing Cl minus. So Cl minus is spectator ion. The volume of the solution equals 0.25 liters, and pKa equal 9.2, so Ka equal 10 minus 9.2. The number of moles of NH4Cl initial is equal to the initial mass, which is 1.24 grams, divided by the molar mass, which is 53.5. So the initial number of moles of NH4Cl equals 0.0231 mole. And the concentration of NH4 plus equal the number of moles of NH4 plus, which is the initial number of mole of NH4Cl, so 0.0231, divided by the volume of the solution, which is equal 0.25. So the concentration of NH4 plus is 0.093 molar. We want to calculate the pH of the salty solution of NH4Cl. The pH is equivalent to the pH of NH4 plus, which is a weak acid. So we return to the formulas of the weak acid, and to find the domain, the formula to be used, we have to compare C0 with respect to Ka. In this problem, C0 is greater or equal 100 Ka, so we apply directly the formula pH equal half pKa plus PC0 equal half pKa minus half log C, so equal 5.12. The correct answer is C. Exercise 28. Calculate the pH of NaCN solution of concentration 0.6 mole per liter. NaCN is a strong electrolyte that will dissociate completely to Na plus and Cn minus of concentration 0.6 molar. Na plus does not appear in any couple acid base, so Na plus does not interact with water. Na plus is a spectator ion. Cn minus is the conjugate base of the acid HCN, so Cn minus is a weak base. Therefore, NCN minus will interact with water to give HCN and OH minus, so the dissolution of NaCN in water will produce OH minus, and pH of this salty solution is equivalent to the pH of the weak base Cn minus in water. So we return to the formulas of the weak base and we compare the initial concentration with respect to Kb. C0 greater or equal 100 Kb, this is valid, and Kb is deduced from Ka times Kb equal Kw, and Kb is equal 16.13 10 minus 6. So we apply the formula POH equal half PKB plus PC0 or half PKB minus half log C, and we found the value 2.51. POH plus pH equal pKw, so pH equal 14 minus 2.51, pH equal 11.49, and the correct answer is C. Exercise 29. What is the pH of a solution by mixing NaOH with HCl? NaOH is a base and HCl is acid, so necessarily we have a reaction. And this reaction is written according to HCO plus OH minus that give 2H2O. K for this reaction is equal 1 over concentration HCO plus times OH minus equal 1 over Kw equal 1 over 10 minus 14 equal 10 to the power 14. So this reaction has a stoichiometry 1, 1, 1, 1. 2H2O can be written as H2O plus H2O. And K for this reaction is greater than 10 to the power 6, so this reaction is complete. To find the pH of this solution, we have to look for the limiting and for the excess. The initial number of mole of HCl equals CAVA equal 2.25 times 10 minus 3 mole or 2.25 millimole. That of NaOH initial equal 2.5 millimole. So at T equals 0, we have 2.25 millimole of HCO plus, 2.5 mole of OH minus. This reaction proceeds till equal infinity, and the excess is OH minus, since the number of mole OH minus initial divided by the stoichiometry 1 is greater than the number of mole of HCO plus initial divided by the stoichiometry 1. So OH minus is in excess, and at T equal infinity, we have traces of HCO plus, and we have practically 2.5 minus 2.25, so we have 0.25 millimole of the base OH minus, so the pH will be basic. The new species in the solution are OH minus in excess 0.25 millimole, and don't forget that we have the ion spectators Na plus and Cl minus from NaOH and HCl. So the number of mole of OH minus in excess equals 0.25 millimole. The concentration of NaOH equal the number of mole divided by V total equals 0.25 divided by 25 milliliter plus 15. Since N in millimole, we can put V total in milliliter, so the concentration equal 6.25 times 10 to the power minus 3. This concentration is greater than 3.2 10 minus 7, so the pOH of the solution equal Pc, and pOH plus pOH equal pKw, so the pH of the solution equal 14 plus log C, and the pH is equal approximately 11.8. So the correct answer is B. Exercise 31. Potassium hydroxide ionized completely in water according to the equation KOH gives K plus and OH minus, so KOH is a strong electrolyte. The initial concentration of KOH equal 10 minus 10 molar, which statements are correct. In this type of exercise, the OH minus provided by KOH equal 10 minus 10, and the OH minus provided by the autoionization of water equal 10 minus 7 molar. So autoionization could not be neglected, and this is the dominant reaction that determines the pH of the solution. So OH minus provided by water is greater than OH minus provided by the dissolution of salt, and therefore we neglect the value 10 minus 10 with respect to the value 10 minus 7. So OH minus in the solution is practically 10 minus 7 molar. We apply the relation pOH equal PC equal minus log 10 minus 7 equals 7, therefore the pH equal 7. Or we can apply directly the relation of the strong base, where we have three domains of validities. In this type of exercise, the concentration of the base given is less or equal 10 minus 8 mole per liter, so directly we can say the pH equal 7. So the correct answer is C.